Hi everyone, today I'll be doing another magnetic field intensity problem, and the problem is as follows. A wire length L along the z-axis, which is right here, from negative L over 2 to L over 2 is carrying a DC current I in the positive z direction, and it's asking what is the magnetic field intensity B at a point x, 0, 0, or somewhere along this axis. Part B is asking, using the result, to evaluate the B field right above the ground plane at point A as shown in the figure. And then the figure is just this, and I printed it on a piece of paper. So let's just start with part A first. So I think one of the most important things when doing this problem is realizing that we're working with a finite wire length L, meaning that we cannot use Ampere's law. So that means that we can use BS law to find the magnetic field intensity. So BS law, as always, is dB is equal to mu naught over 4 pi times I dl crossed with r hat over r squared. So figuring out what we need to use, a typical element in this case will just be a little length of wire, using another marker. And this will of course be dz, because the axis is named z, but you can name it however you want. So in this case, it will just be dz and not dl, because that's a typical element. Mu naught over 4 pi I dz crossed with r hat over r squared. So in this case, what would our r be? Our r. Well, since we're interested at a point along here, somewhere on x, 0, 0, that means this will represent our r. And this will just be called theta. So let's do our cross product. It will be I dz crossed with r will give us a result that is into the paper, meaning that the direction of this will go into the paper. So dB is equal to mu naught over 4 pi I dz. But the question comes, and what angle are we using for our cross product? We all know that if we do cross product, for example, A cross B is equal to AB sine theta. But in this case, it's very easy just to say that we can use this angle, but that is not necessarily the case. What you are interested in is the angle between dz and r. So in that case, if dz is this vector, that means the angle will be this angle right here, which is, you can call it whatever you want. I'm going to call it just theta. That will be the angle between the two vectors I dz and r. But we can, because of trigonometry, we can also use this angle, alpha. I'll just call it alpha. So simply all this means is, I'll write it right here, we can use alpha because we know that sine beta is equal to sine 180 minus beta. And this is simply alpha right here. And again, this is just because of basic trigonometry. So we have two options in this case. We can use I dz sine alpha over r squared, or dB is also equal to mu naught over 4 pi I dz cosine theta, if we're interested in using this angle. And the reason for that again is because of trigonometry. For example, if sine alpha is equal to cosine theta, because sine alpha is simply equal to opposite x over hypotenuse, or x over r. And cosine theta is simply equal to adjacent over hypotenuse, or x over r. So you can pick whichever angle you like, but it's just important to understand which angle you want to use, and it will change the equation just a little bit. You already get sine alpha or cosine theta. So in this case, I'm just going to pick this, but both formulas will work. And again, we did a cross product, and we figured out that the direction is going in. So, moving on to solve this equation. So if you know dB, I'm just rewriting the equation, over 4 pi I dz cosine theta over r squared. So, integrating both sides, we'll get b is equal to moving our constants, which is mu naught I and 4 pi, the integral of simply cosine theta and r squared. In this case, what are the limits of integration? Well, we're interested in this whole wire, so it will be from negative L over 2 to L over 2. So negative L over 2 to L over 2. And going into the paper. So, because the power is 0 on the numerator, you know that this is trig sub. So the rules will be, if you want to do trig sub, is to first draw the triangle. And by a triangle, I mean the one that we're using, which is this one. So this is the same triangle, which is theta right here, z, r, and x. And again, it's the same triangle. The second step is to relate the variable with the constant. In this case, z is a variable and x is a constant, because this x-distance never changes. This point will always be x distance away from the wire, while the z can be changing because dz can be anywhere along this wire. So if we wanted to relate z and x, because z is a variable and x is a constant, then we simply have to do a tangent. So tangent theta is equal to z over x. I simply related the two variables. So because we're interested in getting dz, I'm going to move my x over. So it will be x tangent theta will then be equal to z. Now, taking the derivative of both sides, I'm going to take the derivative with respect to theta on this side, and then the derivative with respect to z on this side. So the derivative of tangent is secant squared, so x secant squared theta d theta, because you took the derivative, is equal to dz. So our third step will be relate the radical with the constant. So in this case, our radical is r, and our constant, again, is x, because x never changes. So to relate that, we need x and r, which will just be cosine. This cosine theta would just be adjacent over hypotenuse, x over r. Now, solving for r, we'll get r is equal to x over cosine theta. And this is just equal to x secant theta. So I'm just going to plug everything back into our integral. Then we first rewrite the original integral that we had, which is mu naught I over 4 pi negative L over 2 to L over 2 cosine theta over r squared dz. So let's just replace our r squared, which we know is x secant theta. So b is then equal to mu naught I over 4 pi from L over 2 negative L over 2 of cosine theta over x secant theta, don't forget that it's squared, times dz. And in our case, dz is equal to x secant squared theta d theta. X secant squared theta d theta. So what's going to happen is this secant squared will cancel out with d secant squared, and the x will be canceled out on the numerator. So again, let me just rewrite it. So what's going to happen is these secant squares will cancel out, and this x will cancel out, leaving us with v is equal to mu naught I over 4 pi. And I'm simply going to move this x outside because, again, it's a constant. The same integral negative L over 2 to L over 2 times cosine theta d theta. Now, solving this integral, we know that v naught is equal to mu naught I 4 pi x. And the integral cosine is simply sine theta from L over 2 to negative L over 2. But we can't just plug this back in. We need to turn it back into, we need to relate it back to the triangle. So sine will simply be z over r. And r in this case is just the square root of z squared plus x squared. So, bring it back in, we get mu naught I over 4 pi x z over square root of z squared plus x squared from negative L over 2 to L over 2. Again, this is simply r. So now we just have to plug in our L over 2. And if you don't remember what to plug it in to, it will be dz. So you look at dz, and you remember that you just plug it back into z. So after plugging L over 2 and negative L over 2, we can just simplify this to make it look a little bit better. And again, the denominators are the same because negative L over 2 squared is equal to L over 2 squared. So we were able to just add these together. Mu naught I over 4 pi x, adding L over 2 with L over 2 will just give us 2L over 2 times over plus x squared, which is going into the paper as we saw before. So to simplify this even further, I can take the 2 out, this 2 out, and then it will just cancel out with this 4 and give us 2 on the denominator. So this would just be mu naught I over 2 pi x times L over 2 square root of x squared plus L over 2 squared. Again, I simply just cancel this 2 out with this 4 going into the paper. And this will be the magnetic field intensity. So, moving on to the second part of the problem. Again, this is just 2 wires now because we placed the original wire on top of an infinite ground plane, which would give us this reflection, because you just have to treat this infinite ground plane as a mirror. And we all know that this type of wire will generate a magnetic field that's going around it, as you remember. So, one way to tell which direction it is going is, you know that if you do a right hand rule, that if you're looking at this point right here, that it's going into the paper, and at this point it's also going into the paper. You can also do the other right hand rule, which is IDL cross with B will give us into the paper. IDL cross with B will also give us the magnetic field going into the paper. So all this means is we can use what we got from part A and simply multiply it by 2, because the effect at this point is going in the same direction, so they will simply add. So the V total in this case will just be 2 times the equation which we got from part A, which is this equation. So this will be mu naught I over 2 pi x. I haven't changed anything, I'm just writing down the original equation. Again, we know it's times 2 because the magnetic field at this point from both wires is going in the same direction due to right hand rule. So now we simply just have to plug in our x. And if you remember, x simply represented the distance the point was away from the wire. So how do we apply it to this picture right here? Well, if you're interested, let's just say we're looking at this little typical element, somewhere right in the middle. Then we know that the distance right from this point to the wire is simply going to be L over 2. This point is right in the middle. And this is because this is a 90-degree 45-45 triangle, which also means that this is L over 2 and this is 45 degrees. And the same for this wire, which is below the infinite ground plane. So all this means is our x will be L over 2. So we just have to simply plug in our x into our formula. So B total, and this is going in, sorry about that, must be 2 times mu naught I over 2 pi times L over 2 times L over 2 over square root of L over 2 squared, because I plugged in L over 2, plus L over 2 squared. Going into the paper. And these two is going to simply cancel out. And this will be our answer for part B.